All right, Miles, good morning. It's Friday morning, August 8th. We're in week five. You're doing the week five study guide right now. I'm going to work through problems one, two, and three. We only got three problems in the homework or in the study guide this week. So I'm going to do problems one, two, and three here now. Okay. So copy and paste them right in here and we'll get to it. Number one is about laminate stacking sequences. So let's talk about this. Identify each of the following dynamics by name and indicate which terms of the ABD matrices will be zero. All right. So hopefully you've looked at the lecture notes at this point and you understand what a stacking sequence is. It's basically how unidirectional fabrics are going to be placed to give you some sort of laminate construction, right? So for instance, here you see 0 plus minus 45 minus plus 45, 0. Um, so that is, I placed a fabric down in the 0 orientation. I do a plus 45, I do a minus 45, I then do a minus 45, a plus 45, and a 0. Okay, so this is all about stacking sequences. All right, and then we have special types of laminates where if the stacking sequences are arranged in a particular order, that we get particular properties of interest from these laminates. So what we're trying to do is we're trying to identify which of these are special, how they're special, and how that's gonna affect the stiffness matrices, capital A, capital B, and capital D. All right. So first, A. All right, we see zeros plus minus 45s. Okay. This guy is symmetric, meaning that if you're symmetric about the midplane. So this is symmetric. And this is also what's called balanced. If you go to your notes or the equation sheet for the class, there's a little bit of like a cheat sheet for this. That kind of shows a bit about special laminates, gives a description, and then tells you what entries of the A, B, and D matrices are going to be zero or going to be affected. So this is directly from the equation sheet right here. And so let's take a look at these. All right, this guy is 0 plus minus 45 minus 45 plus 45, 0. And so that guy is symmetric because the ply sequence is mirrored about the midplane. And that guy's balanced because it has an equal number of plus minus theta plies. All right, so an equal number of plus minus 45s here in this case. All right, so if it's symmetric and it's balanced, then what's going to happen? Well, you can sort of take a look at the chart and we'll see here that the B matrix is going to be 0. And that there are some entries of the A matrix that are going to be 0, specifically A16 and A26 are going to be 0 if this thing is balanced, right? So if you get balanced, A16 and A26 are 0. All right, so let's continue on. We'll cruise this kind of quickly. 0, 90, 0, 90, 0. This guy is symmetric, and it's something called a cross ply. Okay, so symmetric again, B is going to be 0. The B matrix is 0. And cross ply, you get all of this information here is going to be 0. So A16, A26, B16, B26 are 0, but we've already got that covered here. D16, D26 equals 0, and that's all we got. All right, moving on. Negative 30, 30, negative 45, 45. Okay, this one's kind of wild. Um, so let's think about it. Is this symmetric? Well, no. You know, the middle of this guy, it's got a 30 here and a minus 45 here, so we're definitely not symmetric about the midplane. All right. But we do have like equal number of plus and minus plies. So there are an equal number of minus 30 and plus 30, for instance, and minus 45 and plus 45. So this thing is only going to be balanced, right? Which is equal number of plus and minus theta plies. And so the only thing we'll see here is A16 and A26 are 0. All right. Keep moving. D. This guy here is only 0 plies. So we have 5 layers of 0 degree. Okay, so 1, 2, 3, 4, 5 layers of unidirectional material. Okay, so this is a unidirectional composite, right? All the fibers are in the same direction. Fibers only in one direction. So this is unidirectional. It's balanced, it's symmetric, it's cross ply, it's a lot of these things, right? You could classify it in many, many ways. Like all of these definitions fit for a unidirectional, right? So unidirectional composite is symmetric, it is cross ply, it is balanced, it is an angle ply. Okay, so basically all of these things hold true. Anything that you see here is going to be true for a unidirectional composite. All right. So we could write that out, or you could just see what it is there. Um, basically, the B matrix is 0, and then D16, D26, A16, and A26 are 0. There you go. Last one is E. This one's a bit tricky as well. -45, 30, -30, 45. This one is antisymmetric. All right, so antisymmetric is a specific classification as well. Um, but antisymmetric, you have theta and negative theta mirrored about the midplane. So here's our midplane. We have -30 being mirrored by +30. We have +45 being mirrored by -45. Okay, so this is an antisymmetric composite. It's also balanced because we have equal number of plus and minus theta plies, right? So it is both balanced and antisymmetric, this E, right? Okay. And what this is going to be is A16, A26, D16, D26. Okay. So that's this line right here. And then the line below it. This is all 0. B11, B22 equals B12 equals B66 equals 0. Okay, so basically anything that's not B16 or B26, it's going to be 0. All right, so that's number 1 for you. Let's move on. Let's look at number 2. Number 2, you're going to actually start doing some calculation of the stiffness matrices for laminates. Okay, so let's get on with it. Okay, so consider principal in-place stiffness matrix of a thin unidirectional cast matrix silicon carbon fiber lamina. So here's the stiffness matrix of a single layer, right? In principal material directions. Calculate by hand that 1/6 entries of the A matrix, the B matrix, and the D matrix for a composite made from these lamina with the following stacking sequence: 0, 20, 45, 70. A very sort of odd stacking sequence, but okay. 0, 20, 45, 70. Very strange sort of stacking sequence, but okay, it is what it is. Assume each layer is a 0.5 millimeter thick. The 0 layer is the bottom layer. For convenience, here are the stiffness matrices and rotated coordinates, right? So the stiffness matrix at a 20-degree angle, the stiffness matrix 45, the stiffness matrix 70. We have all those given to us, quite convenient. Okay. All right. So let's talk about how to do this. All right, we've got this laminate that is 0, 20, 45, 70. So let's like make a little sketch of this kind of like from the side. Okay, so here's your laminate. It's 4 layers thick. So let's cut this into 4 layers. And you have 0 on the bottom, 20, 45, and 70. These are your orientation angles for this particular composite. And remember how we make coordinate systems for our composites is that we have kind of the X and Z axes oriented this way. The X axis is always sort of in the middle of the stack, right? So this coordinate system always emanates from the center of the stack, right? Okay, given this, we can sort of assign heights to each individual portion of the lamina. So for instance, this dimension here is something that we call Z naught. And this, if each layer is 0.5 millimeters thick, we went down 2 layers. So this is -1.0 millimeters. You can continue with this general process. This is Z1. It's the Z dimension to the start of the second layer. So this is negative 0.5 millimeters. You can do similar things here with this is Z2 is the middle of the stack. So this is 0. This is Z3 just above, so 0.5 millimeters. And then we have a Z dimension of Z4 to the top of the stack, which is 1.0 millimeters from sort of the center coordinate system. All right. So we're going to need these Z values when it comes to calculating the stiffness matrix A, B, and D. All right. So now that we've kind of like made our little sketch here and arranged and shown what the laminate kind of looks like from the side, let's actually do our ABD calculations. All right. So generally, the calculation for AIJ is the summation from K equals 1 to N. K is the layer number of Q bar K, ZK minus ZK minus 1. All right. Right. We don't need to do the full A matrix. Remember, the A matrix is a 3x3 matrix. It's only asking us to do one entry, the A16. So if we want to do A16, this is going to look like the summation from K equals 1 to N of Q bar 16 of layer K multiplied by ZK minus ZK minus 1. All right. So what we do is we just have to add up the stiffness contributions of each of the individual layers. So let's do that. So we have 5 layers here, so K, or 4 layers, so K is going to go from 1 to 4. Okay, that's fine, and we're going to do these summations. So the first layer is Q bar 16 of layer 1. Okay, well, layer 1 is the 0-degree layer. All right. The 16 entry of the 0-degree layer is here. This is Q bar 16 of layer 0. Okay, so the 0-degree layer here, well, it's actually layer 1, not layer 0. It's the 0-degree layer, which is layer number 1, which is 0 degrees, right? Okay, so we're looking strictly at the first layer. So Q bar 16 layer K is 0. And we're going to multiply here by ZK minus ZK minus 1. So for layer number 1, it's Z1 minus Z0, right? This is Z1 minus Z0. Z1 is negative 0.5 millimeters, and Z0 is minus negative 1.0 millimeters. Okay, this is Z0 minus Z1, if that's not clear. All right. That is for the first layer. We have to move on now to the next subsequent layers. So the second layer, I'm looking at Q bar 16 of layer 2. Layer 2 is the 20-degree layer. So we go to the 20-degree stiffness matrix and look at the 16 entry. That's 11.3. So here we go, 11.3 GPa times ZK minus ZK minus 1. This is Z2 minus Z1. Z2 is 0. Minus Z1 is negative 0.5 millimeters. So this is Z2 minus Z1. Right? Okay. So we're going to get some non-zero quantity here. Like this pretty obviously is going to be 0. We can see that, right? This here is going to be non-zero. This is going to have some value to it. Okay. So that's all for layer 2. Let's move on and continue with our layers. So let's look at the third layer. The third layer is the 45-degree layer. So we need the 16 entry of the 45 layer. That's 8.4 GPa. Times Z3 minus Z2. Z3 is 0.5. Minus Z2 is 0 millimeters. Okay. And then lastly, our 70-degree layer. The 16 entry is negative 0.45 GPa times Z4 minus Z3 is 1.0 millimeters minus 0.5 millimeters. Right? Okay, so you work through all this, you crunch the numbers, you'll get A16. Add up all these contributions, 9.7 GPA millimeters. Okay, so we see a GPA millimeter unit here. All right. So that is the A16 entry. You can work through similar calculations for the B16 and the D16. So let's do that. Let's get the definitions of them in here. B16 is 1/2 summation k equal 1 to n of q bar 1/6 of layer k times zk squared minus zk minus 1 squared. So this one's a bit different. All right, so let's go ahead and get on with it. I'm actually going to move the 2 to the other side here. So we have 2 B16. I just moved the 2 to the other side. Is equal to, all right, let's look at, we have 4 layers of our composite. Let's look at the first layer. All right, q bar 1/6 of layer 1 is 0. So just as a reminder, we're looking at the 0-degree layer. And here is q bar 1/6 of layer 1. All right. So here we have 0 GPA. That's the q bar 1/6 entry of layer 1 multiplied by zk minus zk minus 1. So I need z1 minus z0 squared. Okay, so this is going to be negative 0.5 squared minus negative 1.0 millimeters squared. All right, doesn't really matter because we're multiplying by 0, so not big of a deal, but let's be accurate here. All right, the second layer, what's the 1/6 entry of the second layer? Okay, back up here again, that's 11.3 GPA. Multiplied by z2 minus z1. z2 is 0 squared minus z1, which is negative 0.5 millimeters squared. Okay. Plus, we're on to the third layer now. The third layer is the 45-degree layer. So the 1/6 entry of the 45-degree layer is 8.4. This is going to be z3 minus z2. So this is 0.5 millimeters squared minus 0 squared, which is z2. All right. Last layer, the top layer, is the 70-degree layer, not 0.45. GPA multiplied by z4 minus z3 is going to be 1.0 millimeters squared minus 0.5 millimeters squared. Okay, that's generally the calculation. Don't forget about the 2. You have to bring the 2 to the other side. When you do that, B16 is going to be negative 0.52 GPA millimeters squared. All right, that's B16. Let's look at the D matrix. Generally, the definition, D16, this is now 1/3. Summation k equals 1 to n of q bar 1/6 layer k, multiplied here now by zk cubed minus zk minus 1 cubed. General calculation. Okay, so we got 4 layers to work through again. Again, I'm going to bring the 3 to the other side. So we'll have 3 D16 is equal to first layer, 0 GPA for the 1/6 entry. I'm going to go through this a little bit more quickly. Negative 1.0 cubed minus negative 0.5 millimeters cubed. So for the first layer, plus the second layer, 11.3 GPA times z2 cubed minus z1 cubed. z2 is 0 cubed minus negative 0.5 millimeters cubed. Plus the 45-degree layer, here we have 8.4 GPA as the 1/6 entry for layer number 3. We have z3 cubed minus z2 cubed. This is 0.5 millimeters cubed minus 0 cubed. Lastly, the top layer, negative 0.45 GPA times 1.0 millimeters cubed minus Z3 cubed, which is 0.5 millimeters cubed. All right, work through all this. Don't forget the 3 over here. D16, you will get 0.69. GPa millimeter cubed. Okay, so that's calculation by hand of A, B, and D matrix entries. You'll have to do this on the final. Like there's going to be a question about the ABD matrices on the final. No skirting it. You have to be able to do it. You have to be able to calculate by hand something that looks very similar to this. Okay, so understand how to do this, be able to do it accurately. All right, let's move on. Let's look at number 3. Now getting into laminate engineering properties. All right, here we go. Thin carbon epoxy laminate has been fabricated with a stacking sequence of, 092S. So we have 6 layers here, 0, 90, 90, 90, 90, 0. The limit has dimensions of 100 by 100 by 3. Limit has the following A matrix. Okay, here's the A matrix. Calculate the matrix compliance matrix, little a. Make sure you understand why you can calculate the little a matrix as A inverse in this specific case. Calculate the limit engineering properties, and then calculate the strain if it's loaded with a certain load. Okay, so let's take a look at this. All right, the A matrix been calculated for us already. That's nice. We don't have to do all that hand calculation that we just did in the most recent problem. All right, so let's calculate the matrix compliance matrix little a. All right, well, little a is just A inverse, but this only works if the laminate is symmetric. Why is that? Okay, well, generally the relationship between strain and load that you're going to see in your notes over and over and over and over and over is that load and moment, N and M, is equal to, you see this in the notes over and over, A, B, B, D, this laminate stiffness matrix times the midplane strains and curvatures. All right. Generally, this is like a 6x1. This is a 6x1. And this is a 6x6, where each of the A, B, and D matrices are 3x3. All right. This is the general setup. Okay. So if these were fully populated, like if you had all of the entries in here, all of the entries in here, then it is not sufficient to say that the little a matrix is the inversion of the capital A matrix. Because, okay, if you want to invert this, then the midplane strains and the curvatures end up looking like little a, B, C, and D matrices times N and M. This is the inversion of what you just see above there, right? Okay, so this is again 6x1, this is 6x6, and this is 6x1, right? So the little a matrix is a 3x3 portion of this larger stiffness matrix, right? Just like the capital A matrix is a 3x3 matrix within a larger 6x6, right? Okay. Normally, if all of the entries are populated, like if B has stuff in it, if D has stuff in it, if A has stuff in it, then you can't just say that this little a is the inversion of this capital A, because the matrices are 6x6. They're not just 3x3. But in the case of a symmetric matrix, then the B matrix is 0. So when the B matrix is 0, you start to see something that looks like this. Okay? When you see something that looks like this and you do your traditional matrix multiplication, this actually just pans out into 2 individual equations that are decoupled. So if these guys are 0, then with traditional matrix multiplication, n is just a times epsilon, and m is just d times kappa, right? And that's what you have here. So in these specific instances, you get this equation here, which does have a natural inversion, which is that epsilon is a inverse times n. And in this case, we just call this little a, which happens to be the inversion of capital A, only in the case where the matrix is symmetric because you don't have the full 6x6 matrix to invert. All right? Long-winded answer, but generally you need to understand that this can only be done, little a is the inversion of capital A, in a case when you have a symmetric matrix. Or not a symmetric matrix, but a symmetric laminate. Okay? All right, so on with the show. The little a matrix is just capital A inversion. You can do this in MATLAB, you can do this on your calculator, whatever you want. I did it in MATLAB. Away you go, you get something that looks like this. This is the little A matrix, and this is going to be units of 1 on GPA. Okay, so that's part A. Part B. We're asked for laminate engineering properties. Okay, laminate engineering properties, E bar X, E bar Y, G bar X, Y, blah, 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 blah. Okay, these are elastic moduli, shear moduli, Poisson's ratio of the laminate as a whole. In the X direction, the Y direction, so on and so on and so on. Okay, how do we get these? Well, you can kind of look for this in the notes yourself if you'd like, but it's also in your equation sheet, so maybe we just pull from the equation sheet. But your equation sheet will show for you a relationship between strain and load as something like this. This is strain related to load in terms of engineering properties. But also, you know that strain is the little a matrix times n. So if strain is the little a matrix times n, but strain is also all of this times n, then that means that this and this must be little a matrix. Okay? So by that, the A11 entry is 1 on E bar X times H. Don't forget about this H. This H is coming into all of these portions, all right? And you can sort of parse this out fully for all of like the individual entries. Like A12 is just this guy times 1 on H. Okay, and so on and so on and so on. Okay. So you know A11, it's right up here. So you can get E bar X because you know H. All right. As a reminder, this laminate is, we're told, 3 millimeters thick. Okay. So H is 3 millimeters. H is the total laminate height. Okay. So you know H, you know A11, you can solve for E bar X. All right, so you can go through the whole rigmarole, all the calculations to solve for all of these constants. Um, I'll give it to you here. Let me punch it in really fast. And here we go. When I run it in MATLAB, this is what I get. And this is going to be in GPA. So this, and this are GPA. The rest are unitless. All right. So there you go. 159 GPA, 170 GPA, and 500 or 57 GPA. Those are pretty reasonable numbers. Okay. Move on with the problem. Next, if the laminate is loaded biaxially with some forces, determine the resulting midplane strains. Right? So let's look at this. What does this actually mean? Okay, well, let's make a little sketch. Here's your laminate. And our coordinate system, traditional coordinate system. Yeah. We're told that it's loaded with this is an fx, this is an fy, 2, 2, 0. Okay, so fy, here we go. That's this sort of load, 2 kilonewtons, and this way, 2 kilonewtons. This is an fx, and this is fy. Okay, it's tension in y and tension in x pulling this thing. All right, so the question is, what's the resulting strain? Okay, well, we can calculate that. Midplane strain is equal to the little a matrix times n. And these are line loads. So what that means is you need to convert forces, which are just, kilonewtons, to line loads. So we need, what is nx, ny, and ns? And these are simply forces fx over ly, fy over lx, and then this is 0 because we have no fs. All right. What do I mean by ly and lx? Well, this laminate has dimensions, which are here, this is lx, right? It's the length in the x dimension. Similarly, this is ly, the length in y, right? Go back up to the problem statement. We're told that the laminate has dimensions 100 by 100 by 3. So these guys here are ly by lx, lx by ly. It's the length of the laminate in the x direction, the length of the laminate in the y direction, 100 and 100. Okay, so what that means is we can convert loads applied to line loads, which this is 2 kilonewtons divided by 0.1 meters. 2 kilonewtons divided by 0.1 meters, and this is 0. So you'll have that the line loads are 20 kilonewton per meter, 20 kilonewton per meter, and 0. Okay. That with the A matrix, we already have the A matrix, we've sort of calculated already. You can determine what the strain is. So I'm just going to punch that in my computer here really quick with my MATLAB code. Run it, and you'll have strains. Remember, the strains are a matrix. Oh, sorry, this gamma. And here you'll get 35, 32, and 0 microstrain. Right. Lastly, we need a sketch. So from above, we're looking down the XY plane. Let's say that this is your undeformed condition. You have X, Y here. Okay. And then let's sketch the deformed configuration. Okay, we have slightly more deformation in X than we have in Y. So, okay, if X is going out to here, maybe Y is going out slightly less. Right, okay, so let's go about here. It's reasonable. All right. That's it. That's the end of the problem. So more deformation in X than in Y, but not a lot. And that's what's going to happen. I mean, it makes sense that the deformed case is longer in X and Y because you're pulling in tension in X and in Y. So generally, this kind of makes sense. So you like to see that. All right. That's going to be the end of this. I'll talk with you in just a second, actually, here. It's almost 10:30 to discuss the study guide questions. Okay? Chat with you soon.